We are given two functions. The first is f of x, defined as the square of x plus 2. The second is g of x, defined as x squared minus x plus k, where k is an integer. We are asked to find all integer values of k such that the equation f of g of x equals f of x has exactly 4 real solutions. Step 1. Understand the equation. Let's break down what it means for f of g of x to equal f of x. We know that f of x is the square of x plus 2. In mathematical terms, it's a quadratic function, a parabola. And this particular parabola is symmetric about the vertical line x equals -2, which is its axis of symmetry. So for the equation f of g of x equals f of x to be true, there are two cases to consider. Case 1. The inputs to f are the same. The first case is straightforward. If g of x equals x, then f of g of x equals f of x, because we are simply applying the same value to the function f. So our first case is g of x equals x. Case 2. The inputs are symmetric about the axis of symmetry. The second case comes from the symmetry of the parabola. Let's take a moment to review. A function is symmetric about the line x equals k if, whenever the point with x equal to a and y equal to b is on the graph, then the point with x equal to the quantity 2 times k minus a and the same y coordinate b is also on the graph. In simple terms, the graph is a mirror image across the line x equals k. In our case, the axis of symmetry is x equals -2. So even if g of x and x are not equal, the function values f of g of x and f of x will be equal, as long as g of x and x are symmetric around x equals -2. To be symmetric around -2, their average must be -2. That gives us the condition g of x plus x divided by 2 equals -2, or simply g of x plus x equals -4. So, the two cases we will consider are g of x equals x, g of x plus x equals -4. Step 2. Set up the two cases. Let's now plug in the actual expression for g of x, which is x squared minus x plus k into each case. Case 1, g of x equals x. Substitute x squared minus x plus k equals x. Subtract x from both sides. X squared minus 2 x plus k equals 0. This is a quadratic equation. We'll refer to this as equation 1. Case 2, g of x plus x equals -4. Substitute x squared minus x plus k plus x equals -4. The minus x and plus x cancel, so we have x squared plus k equals -4. Now solve for x squared. X squared equals -k minus 4. We'll call this equation 2. Step 3. Analyze the number of real solutions. We are trying to find values of k such that the original equation, f of g of x equals f of x, has exactly 4 real solutions. This will happen if equation 1 has 2 distinct real solutions, and equation 2 also has 2 distinct real solutions, and the solutions from each equation do not overlap. Let's analyze each one. Start with equation 1, x squared minus 2, x plus k equals 0. We use the discriminant to determine the number of real roots. The discriminant is given by b squared minus 4ac. Here, a is 1, b is negative 2, and c is k. So the discriminant becomes negative 2 squared minus 4 times 1 times k, which simplifies to 4 minus 4k. For this quadratic to have two real solutions, we need the discriminant to be greater than 0, 4, minus 4, k greater than 0. Divide both sides by 4. K is less than 1. Now for equation 2, x squared equals negative k minus 4. To have real solutions, the right-hand side must be greater than 0. That's because x squared is always greater than or equal to 0. So we need negative k minus 4 greater than 0. Solving this gives k is less than negative 4. Note that if k equals negative 4, the equation becomes x squared equals 0, which has only one solution. We want exactly 2, so we require k less than negative 4. Step 4. Combine the conditions. Now combine the two conditions. From equation 1, k must be less than 1. From equation 2, k must be less than negative 4. To satisfy both, we go with the more restrictive condition. K must be less than negative 4. Final answer. So the equation f of g of x equals f of x has exactly 4 real solutions when k is less than negative 4. That means the valid integer values of k are k equals negative 5, negative 6, negative 7, and so on.